first of all, let's say several words about me. I'm a professor at Stony Brook University, and a big advantage is that my last name is unique. So if you want to learn something about me or activities at Stony Brook University, you just type my last name in Google, and if you hit Google search, immediately you come to a web page of Stony Brook University, and here many things which I want to share with you. First of all, I want to say that I'm a professor and Frey Family Endowed Chair of Quantitative Finance, and my department is very special in the sense that it's probably the only mathematics department, applied mathematics department, where on board there is a billionaire. So Frey family donated some money for my endowment, and so some fraction of my summer salary or some seminars can be funded from this generous donation. So let's say how we are planning to present today. I will be giving some non-formal introduction to the topics, and then Ray will present a more standard type of presentation with slides, and I will give some motivation and history of this type of topics. So what I'm planning to speak about, I'm planning to speak about drawdown risk measure and applications such as a portfolio optimization and necessary conditions of extremum, which turn out to be beta, which is similar to beta in portfolio optimization. And I want to say that I have been interested in this topic already for quite a long time, like at least for 20 years. And my interest to this topic, drawdown optimization, was motivated my friendship and relationships with my co-author and collaborator, Alexei Chekhlov. Alexei Chekhlov, at the time when I met him about 20 years ago, he was an analyst at a hedge fund. And when he was between jobs, he shared with me some approach which they have been used for allocation of weights in this hedge fund. Usually hedge funds are very secretive, and it's very difficult to figure out what they do, but turned out that Chekhlov moved from one hedge fund to another fund, and actually he has started his own hedge fund at that time. So he shared with me what they did, and that actually was the beginning of my interest in drawdown research. Okay, let's maybe first of all I will share with you what is it about, what drawdown is about, and how drawdown measure is different from other measures. Probably, I'm sure that all of you know what the drawdown means. It's probably the only so-called static dynamic risk measure which is used in the practice. Okay, so typically risk measures are set as follows: that if you have say trajectory of some security like index, for instance, then if it's a forecasted trajectory or historical trajectory, then you just chop these returns in some intervals, like daily intervals, and then you will mess them up together and build a distribution of daily returns, of monthly returns, and then you calculate some characteristics of this distribution. For instance, standard deviation or mean value, or conditional value at risk, which is different between 0 and mean value of the tail, or value at risk, which is a quantile, or CVAR deviation, which is the difference between mean value and mean value of the tail. But doesn't matter what you do, you mess up in one distribution daily or monthly returns, and you lose sequencing of these returns. So what may happen that, for instance, here you may have some consistent going down and doing market, say security going down and down, down, and which would lead to quite significant loss compared to the peak. And this loss compared to the peak is called drawdown. So drawdown could be quite large, but these small consecutive decreases will not be in any way reflected in this joint distribution or distribution of the returns, because these small negative returns may be here around, and they will not penetrate to the tail. That's why basically say actively managed portfolios typically are measured, performance risk is measured by drawdown. So it's a loss compared to the previous maximum. Okay, so that's kind of a main motivation, and that's a standard practice when drawdown is reported by hedge funds or other funds, but usually drawdown is not a criteria for portfolio optimization, except a few exceptions. And this exception actually has been presented to me by Chekhlov, and I want to show with you some results from my joint paper with him. And this paper you can find at my website. If you go to my website and go to publications and search for drawdown, then the first paper in 2005, that's the paper, maybe just a second, maybe there is one more paper, yes. Paper 2003, that's the first paper about drawdown, and it contains approach for portfolio optimization with drawdown risk measure. Now let's say a couple of words about motivation and how I learned about this problem statement from Chekhlov. Basically, what has happened that in their fund there was there were many heavily correlated strategies in futures markets, such as silver and gold, and they mostly were built with the same principle. And so they had a tendency to losing money at the same time. So the question was how to allocate money between funding between these strategies. And that's basically what they have done. They have assigned some weights, and then they did a simulation for the long time and observed how this strategy behaved together. And then they measured some characteristics such as a drawdown and return. And then they sampled many times until they find some combination of weights where the strategies perform reasonably. So it's a kind of a brute force optimization allocation of weights across the investment strategies. And now you see here, say, actually, that's a table and which shows the investments in the strategies. So it was minimal investment, say 0.2 in every strategy, and then it's going up to 0.8. So these are quite heavily leveraged strategies, because if you have here 20 instruments multiplied by 0.8, it would be like a 16 or 17 leverage. So it's a highly leveraged portfolio. And you see here there's a risk return quite favorable. That say if they set up 6% drawdown, that they were able optimize the strategy such times that they would get 44% of return. And it was not so far away from reality. They actually had a quite consistently over 20% return for many years. Okay. Now, but actually, I quickly realized that it's possible to make a much better procedure and formulate the problem as a portfolio optimization problem, where you would formalize what the drawdown is, what is the return, and do portfolio optimizations. That's basically what has started this type of research. Now, so that's some that I'm showing you the paper from. Now I'm showing you some different paper from my website, which is about portfolio optimization with multiple sample paths. With the first paper, we have considered only that there is a one sample path and you optimize weights to one sample path. And then we realize that if you do sampling, then you don't know exactly what would be the sample path. So there would be portfolio optimization over say most conservative drawdown over the multiple sample paths with a constraint on return. So that's one more paper. And then the further evolution of the project was that we started interested in some further characteristics of this risk measure. And in particular, one of the most important characteristics is so-called portfolio beta. And for standard risk measure, mean variance, the portfolio beta is a correlation with the market. And again, since variance is messing up the returns, the correlation of the market also correlation of the instrument with the market, which is a beta, also cannot pick up these consistent losses in the portfolio. Okay. And also at that time, we already knew that if you have a portfolio optimization problem, then there is a kind of straightforward way to generate betas. And we already at that time had a paper with Rockefeller on optimality conditions in portfolio analysis with generalized deviation measures, where we showed that actually beta is a necessary conditions of extremum, and all betas whatever were known by that time were just following with necessary conditions of extremum. Let's maybe show you a couple of such several betas. For instance, standard beta is a covariance of rate of return with rate of return of market and then normalized. And if you have a conditional value at risk, then beta is here. All betas are here, but here is a beta for conditional value at risk measure. Then it appears that you take in the numerator underperformance of the security with respect to the market condition that actually the market is in big trouble. So market is below some value at risk. Okay, so basically conditional value at risk is kind of conditional measure of loss, conditioning that market is down, and then this beta is analog of standard beta. And we knew that we could obtain this beta as a optimality conditions, similar like a gradient equals 0, that optimality condition in standard unconstrained optimization problem. And we have used that optimality condition, obtained beta for portfolio optimization problem with drawdown risk measure. And it turned out that this drawdown beta has a very nice engineering meaning, not only mathematical meaning. It's not only not only necessary conditions. And and I want to show you just in fingers what this drawdown beta means. Basically, the idea of this beta is that suppose that beta equals -1. It means that if market loses, say, 10%, then security should make 10%. Okay, if say I mean, make from the point of view of drawdown. All right, let's explain to you, for instance, let us show you a graph of security which has drawdown beta equals -1. And if you would have a look here, say that's a crisis of year 2008, okay, then you observe that from the peak market lost in uncompounded cumulative return about 70%. And the security at that time gain about 70%. Okay, and it's just an example how security with negative beta, which is equals -1, behave. Okay, and the beta, drawdown beta, it actually equals to the ratio of how much security makes in numerator, and in denominator how much S&P or some other index loses. If you are speaking, say, about maximum drawdown. If you are speaking about conditional drawdown at risk, which is the average of the worst case, say 5% or 10% drawdowns, then you take average of worst case drawdowns and place it to average of returns of security when S&P is in worst case, say 5% drawdowns. You take say loss of S&P 1, loss S&P 2, loss S&P 3, whatever drawdowns are, and sum them up and put it in the denominator. And in numerator, you take a gain of security corresponding to this loss, gain of other security corresponding to the loss, sum them up and put it in the numerator. So roughly speaking, it directly answers the question how much security is gaining while S&P is losing during drawdown. Okay, so just ratio, as simple as that. And that's this has been published in the paper with Zabarankin and with Chekhlov. But here we are working with a worst case, say 5 or 10% drawdowns. But but sometimes you're interested in, say, in drawdown just exceeding specific threshold. And that's the most recent paper which we are currently writing together with Ray, my co-author, and we about finalizing this paper. And this risk measure is called ERAT, expected return of drawdown, and there is also beta corresponding to expected return on drawdown in excess of some threshold. one of the strong motivation for that was to build a practical tool where you would be able to actually measure performance of security during the previous drawdowns, say if measure the beta, or if you forecast returns of security, what is a forecasted beta. So we have built a website which I'm trying to find. That's a website. How you get to this website? If you search my last name and go to research, then the first link will be Drawdown Beta, and that's Drawdown Beta. And Drawdown Beta contains betas for tickers, S&P 500 tickers, based on 10 years history and 15 years history. And you could observe that the standard beta and this type of betas are quite different. So CDR beta is beta corresponding to worst case 10% of drawdown, and ERAD beta corresponds to the non-zero drawdowns. So ERAD beta more stable in the sense that it takes into account all possible drawdowns, and CDR beta only several drawdowns corresponding to biggest percentage of drawdowns. And if you would, for instance, punch some ticker, for instance, MSFT, find a ticker, then you would see that actually, say, over the 10 years history, that ERAD beta is slightly negative, around 0. CDR beta slightly positive, but standard beta is bigger than 1. It means that on monthly basis, correlation is very high. But now if you would check how Microsoft behaved during the drawdowns, then you would observe that actually Microsoft behaved quite well, and it didn't lose money during drawdowns, at least from the point of view of this drawdown definition from the point of view of drawdown beta. And Ray will explain and show you in more detail how is everything defined and so on. So basically, that's what I planned to share with you, and we are very much excited about this risk measure, and we see a lot of practical applications for these drawdown beta concepts, and it's getting actually more and more popular every day. Okay. All right. Basically, my informal introduction. So now maybe Ray can pick up and discuss in more formal setting what I have shared with you.
Thank you, Professor Uryasev. So I will be using these slides, and there's a lot of iterations from what has been said, but there's going to be more like detailed explanations of how we built this website and how this model is developed. So first of all, just some quick definitions. As we have seen, the drawdowns of a simple path is defined using the vector of uncompounded cumulative returns. Here we are using the uncompounded cumulative returns, which is a sum. There's also a way of doing it with compounded returns. So we first define this variable W as the cumulative returns, and the drawdowns will be defined as the difference between the historic peak in the cumulative returns and the current cumulative returns. So a picture that will demonstrate this idea is this one. So basically, for any point, you will find the historic peak and you take the difference here. Since everything is uncompounded, you can basically just sum the difference in this period. And I also plotted a historic S&P underwater curve. So these red regions shows you the drawdown periods throughout this history. And there's another definition, which is conditional value at risk. So for a random variable x with a confidence level alpha here, alpha is usually a large number like 0.9 or 0.95, which will correspond to the 10% and 5% tail. The CVAR is defined as, there are several definitions. We are going to show two of them. I think this one is defined through a minimization problem where the C is going to be a sufficient statistic. And it turns out that if you solve this problem, the C will be equal to the value at risk corresponding to the same threshold alpha. There's also another definition through a maximization through a expectation with a maximization on the Radon-Nicolin derivative. So this will be using a Q that is stands for indicator, and the Q's will be 1 divided by 1 minus alpha for all those that are the 10%. Say alpha is 0.9, then those will be 1 divided by 1 minus alpha for the 10% largest drawdowns, and it will be 0 for everything else. So it's basically an indicator function that points to the largest drawdowns depending on which threshold you pick. Here we use the definition for CVAR to introduce this what we call CDAR. CDAR is basically the CVAR of the drawdown random variables. So if you have a sequence of returns and then you compute the drawdown observations, you can compute the CVAR of those drawdowns, and then it gives you the CDAR of your return of your cumulative returns. So as we can see, there's a close connection between CVAR and CDAR, and we further can define this for multiple sample paths. Here, suppose we have S sample passes with PS indicating the probability of each sample path, then we can use this maximization, this dual problem, where you maximize this Q in the risk envelope, and then you can get the CVAR of the drawdowns again. This is basically, the definition we have shown above are basically extensions from the risk envelope theory developed and the risk quadrangle theory developed by Rockefeller and Uryasev. I will skip these details, I think. And an important fact that is proved by a 2004 and 2002 paper shows that there's an equivalence between optimization problems of CVAR and expected regret. So the idea is that if we look at, first we make some additional notations, we define an expected regret of a function with the threshold C as this one, GCX equals expectation of X minus C. This plus is the indicator function of the positive. So if this is basically a ReLU function if you come from deep learning. The notation here, F alpha XC, this is exactly the formula that we saw inside the minimization function for the CVAR. So basically, if you have a random variable X with the distribution function F, then the CVAR is the minimum over C of this F alpha XC. And if you're trying to minimize the CVAR, then basically what you're doing is a joint minimization in X and C of the F function. So what the 2004 paper by Tesori and Uryasev proved is that there's some conditions under which you can state that these two optimization problems are the same. So basically, for every optimal point for the CVAR problem, there will exist a pair such that it is optimal for a expected regret problem, and for any threshold C and a optimal point for the regret problem, there's also a unique threshold alpha such that this will be such that this maps to a optimal point for the CVAR problem. So basically, there's a mapping between an optimal CVAR problem to an optimal point of the expected regret problem. So from what we have said before, if you have any like a CDAR beta that is defined based on a percentage alpha, then there's exists a problem that is based on a threshold C. The only problem is that you don't exactly know what that is before you solve the problem. But basically, every time you solve a problem with a threshold, you know that you're solving a problem with a CVAR risk level as well. So based on this idea, we extended the work of the Brankin et al. In 2014, which developed the CDAR CAPM framework. The problem that we are solving is basically that we are trying to, so let me just go forward a little bit. So this one is the zebra rankings problem. They are trying to minimize CDR subject to this expected regret constraint. So this is a variation of the traditional CAPM framework. So what they did is that they switched the risk function that is using Markowitz portfolio optimization. So the variance is now replaced by a CDR risk functional. Just recall the definition of CDR here is CVAR of the drawdowns. So what we can do again is that we can switch this risk with the erode, which we call which stands for expected regret of drawdown. As we have seen, this is basically a function that takes positive values, and all the negative values will be 0. So this will be our new risk function that we can place in the portfolio optimization problem. So what we can formulate is that we can solve this problem instead. This gives us a erode-based CAPM problem from which we are going to derive the beta values that we are going to call them erode betas. Just a quick reminder that the CAPM is I assume everyone is very familiar with the CAPM setting. So we are going to apply some risk functional here. This is the standard CAPM model. We are going to apply some risk functional, and then the market portfolio is assumed to be the optimal portfolio, and that is exactly why we use the S&P 500 and some other indices as a market portfolio in our experiments, and they will be used as the optimal portfolio in the beta calculations. So here is I'm going to first talk about the zebra ranking results. So they derived some necessary optimality conditions for the CDR portfolio optimization problem, which is the one in 7. So for this one, it is shown that the optimization criteria will be this formula, which relates the cumulative returns of the optimal portfolio and the cumulative returns of every stock. So here I is the stock index. M stands for the market portfolio. They are related by this beta, which we call CDR beta. Remember that this will differentiate for every alpha level that you pick. So there's an array of these beta values based on the alpha that you chose. The Q here is the due variable that is again an indicator function for the largest like say 10% drawdowns in the optimal portfolio, which here is the market portfolio, and 0 otherwise. So the beta here, so we're going to look closer at the beta formula. It says that it's going to have a denominator that is basically the sum of the 10% largest drawdowns in the market portfolio. And on the denominator, there's going to be these differences. And these are the difference in the cumulative returns of the stocks in the period where the market is in a drawdown, is in its actually 10% largest drawdowns. So basically, it's going to be a one-to-one correspondence in every of these differences. But on top you have the difference in the stock index, in the stock, and on bottom you have difference in the market index. And if you sum those together, you get the beta CDR beta. And the CDR beta is going to be extended to the erode beta, which actually shares very similar properties.
Ray, can I additionally comment that in numerator, as I explained, that there is Q, which is an indicator function, which is exactly picks up returns corresponding to the returns when the market is in drawdown. So it's just implementation of what I have explained to you with the graph. I want to emphasize it. Okay, go ahead, Ray.
Yeah, so it's very important to actually remember that CDR will pick up only the largest. I'm using an example of alpha equals 0.9, so it will basically pick up the largest 10% drawdowns. But in the erode one, it's going to be an indicator of something else. Actually, it's going to pick up all the drawdowns that are above the particular threshold you chose. So for example, let's say that our erode is based on threshold epsilon. Then here, again, we have this beta formula. On top and bottom, you have a one-to-one correspondence of the differences again in the cumulative returns, but now your indicator function will pick up only the drawdowns that are above this threshold. Say if you have epsilon equals like 1%, then it will only pick up those drawdowns that are larger than 1%. So this is a very intuitive way of understanding, because most of us care not about like if you're in the 10% largest drawdown throughout the history, but we're more concerned about the exact magnitude of the drawdown. So this threshold will be a better way of evaluating our portfolio if you're a manager. So for example, I only care about drawdowns larger than 5%, then I will apply this formula with 5% in the epsilon. And this beta will give me a more meaningful value than if you use something like 10% largest or 5% largest, because these are more relative than the thresholds. So again, we here is there's some abuse of notation. I think this erode actually not stands for the same erode, because we don't have this minus epsilon here, but it means that we're picking up all the drawdowns in the market portfolio that is above this particular threshold. And similarly, we have on top for each stock, for each ticker. And then we can compute all these beta values, which we call erode beta. So what we can show next is that there's also a similar formula for the single pass. Remember that this one here, because we're summing over PS, this is a multiple pass setup. There's a very easy way of looking at the single pass is just without this additional sum, you have basically this formula where everything is simply an indicator. I will go on to give some numerical results. As mentioned, everything is posted on the web, and we implemented the formulas we have been discussing. So mostly this formula for the erode beta, and similarly for the CDR beta, we have the single pass formula. So on the website, we're going to display every of these values. So here we particularly chose a threshold of 0 for the erode beta, which simply means that you're only looking at all the non-negative drawdowns, only all the positive drawdowns. So remember that drawdown is never going to be negative. So this means that we're just eliminating all the zero drawdowns. And then we compare it against the CDR 0.9 beta, which is looking at the 10% largest drawdowns in the history. And here is the standard beta, which is based on variance. And we also show some other metrics like the max drawdown, annual return. This U ratio, it's I think I have a definition later. Actually, now the U ratio is it's another ratio that it's going to, let me find the, yeah, so it's if you look at this website, here's the definition of the U ratio. It's the average daily return, basically divided by average drawdown and divided by average length of drawdown. So this one is the average daily drawdown. So basically here's a division of average daily return divided by average daily drawdown. And let me go back to my slides. So first, we can look at some particular stocks, which is very interesting. Here we have Netflix. This is a very particular example of that it is actually not having a drawdown in the period where the market suffers large drawdown. Here we can first look at these numbers. So the calculation shows that there's a large negative erode beta for Netflix. It's negative 3.5 from January 2006 to January 2021. And this period includes two major crises, the financial crisis in 2008 and the COVID crisis in 2019. As we plotted the uncompounded cumulative returns in these two plots, it's easy to observe that when the market, which is the one in orange and its drawdowns in red, is having large drawdowns in 2008, Netflix is the one that is actually gaining a lot. And it has very small drawdowns when the market has large drawdowns during the recent COVID crisis. The CDR 0.9 beta has negative 2.388 for the same stock. it's a slightly smaller value. It only, remember that this only looks at the largest 10% drawdowns in magnitude in the history. So mostly will be somewhere here. And the interesting thing is that the standard beta for this stock is actually positive as 0.862. So it doesn't really indicate the effect that it has a hedge against the market drawdowns as we see in the plots. So this is one example where Netflix actually has a different sign for erode beta, CDR beta, and against the standard beta. Similar example is a STT. STT has also both negative betas for erode beta and CDR beta, but a positive beta, a standard beta of 1.4, and the plots are quite similar to what we have seen for Netflix. And I think another example is Amazon. The numbers are negative 1.17, negative 0.25, and standard beta is 1.3. So we actually summarized some of the results for all the Dow 30 stocks. This is based on two periods. There's a 10-year period and the 15-year period, which actually overlaps. The 15-year period goes 5 year back. So as we the table shows all the different values of it, and we actually calculate some correlation coefficients between the two time periods. So the numbers summarized here shows you a correlation. This correlation is across the stocks in this particular market index, and across the two time periods of 10 years versus 15 years. And it can be seen that we have higher correlation in all three betas for those that are in larger stocks. So particularly the Dow 30. The Dow 30 has a much higher correlation than say the SP 500. And also for this case, the erode beta is actually more stable than the CDR beta, in the sense that this correlation number is higher, but the standard beta is still by far the most stable metric. So by stable, we mean that this number doesn't change a lot during different time periods. If we go on to use actually two different time periods, so here in table 4, we have two non-overlapping time periods, the one from 2006 to 2013, another from 2013 to 2021. It's again showing you that you have higher stability in those beta metrics for large stocks, but not for those small stocks that are like smaller stocks if you look at SP 500. And I think this is almost everything I want to talk about. And the last thing about it is that the erode beta has another attracting property that it can be used as a constraint on top of other portfolio optimization problems. For example, if you look at the standard market portfolio optimization problem where you maximize the cumulative returns in some historic period, subject to a variance smaller than delta, you can add a constraint based on the erode beta or the CDR beta, so that you can ask for this erode beta equal to 0, and this portfolio optimization problem can actually can also be solved, and this is a future perspective of the work. So just to conclude that we have built upon a CDR CAPM problem, which was a natural extension to the original CAPM problem. The CDR problem is further extended to an expected regret problem because we have an equivalence relationship that was shown by earlier work. And so we can derive a set of betas for every chosen threshold of market drawdowns instead of a percentage. And setting the threshold 0 will give us every drawdown at risk based beta. We computed numerous numerical experiments, and the new erode beta provides more interpretability as well as some interesting insights into hedging against market drawdowns. And we posted all those results on the website. And here are some main references. Thank you very much.
Okay, wonderful. Thank you, Ray and Stan, for the very interesting talk. If you have questions, please do type them into the chat. I don't see any at the moment. So while we're waiting for the audience to gather their thoughts to put in some questions, maybe I can ask a couple that came to mind. So I was actually going to ask about this U ratio, but you eventually did put up a definition. So what it was the average return divided by the
Yeah,
average daily drawdown return?
Yeah, average
Or
daily
sorry,
return.
okay.
Average daily
Average
divided
daily
by
return divided
average.
average
At
drawdown,
average
daily
daily
drawdown.
drawdown.
I see. Measured in the sense of the average drawdown divided by the average length of drawdown. Okay. And what's the intuition as to what this, like, what exactly, I guess you would obviously like a large U ratio because you'd want a small average daily drawdown relative to the average daily return. So you want that ratio to be large, but is there some way to gain an intuition for, what's a sensible number to have? Like, I see various numbers here, but I don't know what, is 0.46 particularly bad, or is that decent?
We have not actually studied that. We have posted it at the website. Maybe Ray, maybe go to the website and just order it by this column, and we will see what the values are.
So Microsoft is particularly high there, right? It seemed to be at the bottom of the list. Yeah, sorry, the top of the list now,
it's
right?
on the top of the list. So the range is from 1.5 and go down, or click it again. So we will see from 1.5 to near 0, 1.15.
To near 0.15.
So it's a daily return divided by daily drawdown, something like that. So.
Okay. Well, I mean, if you haven't really thought too much yet about it, then, we probably can't come up with an immediate response, but that's okay. I was just curious about it. It's a very interesting measure. There is a question in the chat, and Dan, would you like to unmute yourself, turn on your video, and ask away?
Sure. Hi, Stan. Great to
hi, Dan. So happy to see you.
If at least through video.
Yes, hope to see you in person then shortly.
Yeah, that would be great. I have one question for you, and this is really great. So drawdown is typically, it's not typically, it's used as an ex-post measure of risk or loss, right? I mean, it's really something that is used through performance. And as you think of using it through optimization, because I have thought about this for a while, I'm sure you have started. The main issue to use it for optimization is you want the optimization to be ex ante, right? Like you want it to make sense of a forecast of what will come later in terms of risk, and which means that the drawdown will be very, very heavily dependent of whatever simulation models you use to forecast returns, right? I mean, the main issue why drawdown is I think very interesting is because it captures a little bit of the, at least at some point in time, some autocorrelation of returns, right? Of the fact that, as you say, that maybe you have many of them happening at the same time. If everything was independent and perfectly random and independent, you probably you wouldn't have it wouldn't be as meaningful, right? So how do you see it used for optimization and how would you do it in practice? And do you have any experience on how it behaves and out of sample, for example?
Yeah, maybe I can comment. As you pointed, result very much depends upon how good your model is. If your model, like your model daily return, which don't have all these persistencies, then you just do not observe these persistent consecutive losses. But if you do some historical simulation, when you say chop, say monthly returns or some quarterly returns, and you put them together in different sequences, you could observe drawdowns. So we observed a reasonable measure of drawdown which has been forecasted. So we could take historical returns and adjust expected mean values. and it picks up. So, but it's not a matter of optimization, a matter of correct modeling. And then if you do correct modeling, then it will pick up good weights, which would control, say, average drawdown, or conditional drawdown at risk, or error. But everything is boils down to correct modeling of drawdowns. Okay.
But it's going to be heavily dependent, right, on whatever model you use for forecasted returns, right? Because that's a key thing. So what you're saying is that one reasonable way is to use historical returns and maybe use some bootstrapping or something like that to do that, so that you capture some of those so those autocorrelation, at least historically, in the modeling as a reasonable way of doing it.
Yes, so if you take, say, quarterly or monthly, then at least on monthly basis is autocorrelations are kept together. So,
okay, I get it.
Not bad way. Maybe if it's on autocorrelation on monthly basis, are lost because you're messing up months, but you're not messing up days. So, to some extent, you keep reasonable projection what's drawdown may be happening over different trajectories.
Okay, thanks, Stan.
Okay, thanks, Stan, for the question. And we have another one. Uryasev, would you like to unmute yourself and turn on your video to ask your question?
Hi. So actually, I have two questions. One is, if this U ratio is the daily return divided by the average drawdown and the length of the drawdown, how can we use with the Sortino ratio of the with U ratio? Will it make sense? And if we look at this EROD beta and CDAR beta, so would it make sense using these values hedging in derivatives for the particular assets or securities?
First of all, you mentioned Sortino ratio, right?
Yes.
I think Sortino ratio is still messing up returns, right? It's remind me what the Sortino ratio is.
So Sortino ratio is basically is the ratio related with the drawdown. It's so it's the basically risk adjusted return of an investment asset or a portfolio or a strategy. It penalizes the falling part. Instead, Sharpe ratio penalizes also positive returns. Sortino, it only penalizes the negative returns.
Yeah, so I'll just interject. So it's basically Sharpe ratio, but the volatility that goes in the denominator is the volatility of the downside of things that underperform the expected return or the
downside deviation.
Yeah, so it's not drawdown. It's actually you're summing up say daily returns. So it's not type of ratio which we're working here because it doesn't pick up consecutive correlations of securities first, and second, the beta is actually a measure how security behaved during the market drawdowns. Okay, it's a relative measure. It's a portfolio performance measure, right? It's just you want to laugh when everybody are crying. Means that market is going down and your portfolio is going up. So you want your portfolio drawdown beta be highly positive. Okay, that's exactly what you want. And so beta reflects these specific important characteristics. Okay, It's a unique characteristic. I have not seen such type of characteristic so far.
Okay, I don't see any other questions in the chat, but maybe could you? I'll ask one more quick one. Can you go back to your slides? I think it was equation 11. I don't recall which. Sorry, equation 7, where you define the problem that you're looking at. Yeah, 7 and 9. If you maximize it a little bit, I just want to make sure I'm understanding the problem formulation itself. So you're trying to, let's take equation 9 then, I guess. So you're trying to minimize the EROD. W of X represents the sequence.
Cumulative returns.
The cumulative returns, okay. The EROD of the cumulative returns such that PS WST of X. So what is WST?
So basically here we're looking at a multi-pass formulation. If you're looking at the single pass, there's not going to be this sum. You just have WT, which stands for the terminal cumulative returns. And X is the allocation.
Okay, so you're trying to you have a minimum expected return that you wish to have.
It's a regret.
That's what this would be interpreted as, I guess. And then you expect the EROD of the WX. Okay, so now I guess the question I had about using drawdown, it's kind of, maybe it's not a trivial question, but is there issues with time consistency of using this as a performance criterion? And I presume, of course, if you have the sequence of drawdowns, they're not independent of one another, right? Drawdown in day 1 is not independent of day 2, and so on. So how do you resolve any of these issues? I mean, these are perhaps part A and B of the question. So time consistency of the criterion, and
I always thought of time consistency if you're predicting something, but we're not doing predictions here, I think.
No, not time consistency in terms of predictions, but there's a notion of if you're solving some sort of optimization problem and you solve it at time 0, and then you get some optimal strategy. In this case, your strategy, I guess, is just portfolio weights.
Again, so if you have variance, then it's also not time consistent.
I agree. That's right.
Yeah. So, but we are simply replacing variance here with another risk that is weight.
Maybe can I comment a bit about setting? Basically, it's a good model of so-called constant proportion strategy, because here weights are, you set up weights and you run these weights for a very long time without changing weights, okay? So there is no problem with this time consistency, because you actually not making a decision along the way. You decided, say, 5 years ago that you will be having 60-40, and you keep running and running and running without changing the allocation, okay? And
right, so it's a static optimization problem.
So it's a dynamic static risk measure, in the sense that static, that you do not change the strategy, and dynamic, it means that you are running it for quite a while, right? It's not like consistency when in stochastic programming, you at every time moment you have a possibility to do this and that and so on. There is no anything like that. It's a model of constant proportions portfolio.